Okay. Okay, so our next speaker is Steffen Bollman from the Max Planck Institute for Solid State Research in Stuttgart. And he will talk about time reversal invariant topological superconductor in the Coulomb blockade regime.
Okay, first, thank you for the organizers for the chance to present my work about time reversal invariant topological superconductors in the Coulomb blockade regime, which is work I do together with Superconducting and William König. And so let's get right into that with the motivation. So I think this is a well-known fact that topological features in the band structure of materials lead to via the wide boundary correspondence to zero energy edge modes. And here we have a famous example, which is a P-wave superconductor, the DIII chain, that has these Majorana edge modes on the edges, of course. And these are interesting systems by themselves. But what if we add interactions to that? And one famous example for that is, for instance, the tetron. So this is just a setup where we have two of these DIII chains. So we have four Majorana edge modes. These two are coupled by a Josephson junction together. And most importantly, we have here these charging terms. So adding charge to the island costs energy, or we can apply some gate voltage and have some background gate charge in G. And what it means is we can very precisely fix the number of charges on these islands, if EC is large, of course. And say we put an odd number of charges on there that comes with a constraint on our Majorana edge modes that looks like this. And using this constraint, we can actually build up quantum gates via bilinears of these Majorana edge modes. So these fulfill a Pauli algebra. And now we have a perfectly fine qubit. And even more, what you can do is, and what was first done by Majorana Cooper, they considered exactly such a setup and coupled leads to it. So they allowed hopping from electrons onto the island. And what they found that the effective low energy Hamiltonian of the system is an OM Kondo impurity problem, where M stands for the number of leads that is coupled to this island. And in the special case where M is 4, this corresponds to a two-channel SU2 Kondo. And for further references, this is the important case. And exactly because of this, I'd like to discuss the two-channel Kondo problem. But first, let's start with the one-channel Kondo problem. So we have this Kondo Hamiltonian consisting of a free electron gas coupling at one side to a magnetic moment, like here. And if we now look at the RG flow of this coupling constant, we will see that it flows to strong coupling, meaning these two objects here, so the spin on this side and the free momentum, they will form a tightly bound singlet, and this electron therefore screens the free momentum. We have just a scattering center for the rest of the electrons, and eventually end up with a Fermi liquid. The setup changes a little bit if we have a two-channel Kondo problem. So we have now two free electron gases coupling to this moment, where again, if we do an RG flow, it now depends which of these is larger. So the one that is larger will again flow to a strong coupling, and the free moment will again form a singlet state and get screened. However, if they are fine-tuned at exactly the same, the system cannot really decide with which of these two electrons it should bind. And we end up with a quantum critical point where fractional excitations do the talking. And this system actually was already solved by different methods. So for instance, there was the beta ansatz solutions, or people tried conformal field theory. But I would like to discuss a particular one, which is the Emery solution. Now, unfortunately, yes. Say what? Say again?
Along the top.
Yeah.
Yeah.
Here.
Hide video panel.
Hide video panel. Okay. No. Didn't really work. Okay. Anyway. Here we are. Okay, the Emery solution. And what they did was using a sequence of bosonization, so mapping the electron problem to a boson problem, then transformation and referminization to map it to a purely to a Hamiltonian consisting out of Majorana fermions, where we have first these 4 Majorana fermions that corresponds to the lead electron, but now a fractionalized representation of it. And also they map the spin to Majorana fermions A and B. And what we now see is that only one of the 4 Majorana fermions is coupling to the impurity anymore. And so here we have our fractional excitations. And therefore, let's just talk about the impurity of the island. This goes like the log of G, where of course we know from statistical mechanics, the impurity is, the entropy is something like the logarithm of microstates. So we can understand this as the dimension of our ground state manifold. But funny enough, this can be this can take non-integer values. So we have a generalized quantum dimension. And for one Majorana fermion, G is the square root of 2. Okay, perfect. So since we now understand the 2 the Kondo, let's come to our system, or what we're looking at. And this is first of all a 2-fluid model of a time reversal invariant superconductor, triplet superconductor, or short TRITOPS. This is a one-dimensional system. We consider it a 2-fluid model. We have the electrons and the order parameter that consists out of this n vector, what I call the Cooper pair orientation, or orientation of the order parameter, and the superconducting phase, as well as this derivative reflecting the p-wave nature. So even derivatives, so we have an odd derivative, so we have an even spin factor, therefore spin triplet. All right. Okay. This n vector we'll assume to be real, and it can take values all over the sphere. Here we see, for instance, the periodic table of topological materials, and we are in the D3 class in 1 dimension. So we have indeed a topological invariant, and therefore also edge state, which are then Majoranas. And since we have time reversal symmetry, these Majoranas come in Majorana pairs. And in contrast to the regular TRITOPS chain, now we have 4 Majoranas on our chain, so 2 at each edge. 2 at each edge. Right. So, and what is now if we allow for fluctuation in the order parameter? Well, this was investigated by Michael Ram in 1+1 dimension, but we will put it consider it as a quantum dot, and so we will work in 0+1 dimension, and this is pretty much
just for clarification. N is the G vector of
yes.
the bulk.
Poorly named, yes, but you're right. N is a D vector.
So this is like an A phase with a unidirectional D vector.
Yeah. Okay, so I said quantum dot. So what we do is we take one of these wires, one of these superconductors, we put it on an island where we again have charging energy. So with a total charge, so this number of Cooper pairs, and this is a fermionic charge. And additionally, we also have the fermion spin and the angular momentum. That is, so that is the canonical conjugate to this n vector, right? And this is a term that is more ad hoc. So how do we solve this problem? So what we do is we make a transformation in the co-moving frame. So we take an electron and we take away its charge and also orientate the spin so that we have a charged electron with a well-oriented spin. And we choose against all other conventions the y direction, but this is for computational convenience. And what happens is that we actually can get rid of all these. So since they have no charge, we can get rid of the charge in this term. We only are left with some generalized angular momentum of the condensate, what only feels the background field of the spin of the fermions anymore, of the spins of the fermions. And we completely get rid of this order of the spin and phase part of the order parameter and end up with this Hamiltonian. So we have our island. Here we now have perfect TRITOPS superconductors or TRITOPS chains, but in each spin sector 1. So we have 2 copies of the TRITOPS chain and spin up sector and spin down sector. And all our interactions are only concerning the condensate anymore. And since that, we can actually solve the whole thing and find the spectrum. First of all, that you can see here. And we are later on mostly interested in this parabola, like this is namely the case for an odd number of charges on the island. And what we find is that G is odd, so we have a 4-fold degenerate ground state with two degeneracy coming from the Majoranas, what I will later on call now orbital space, and a 2-fold degenerate from the J vector, from the angular momentum. Very well. So now we have established the Majorana Cooper pair box, so this quantum dot here. We can go on and couple it to leads, and then we do just by adding this term. So we have lead electrons coupling to the Majorana fermions, and since these are charge and spinless, we also need to insert charge transfer and a spin transfer in here, and this is in the term. So what we want to do is a low energy theory. So we only consider processes of second order because our charge is well defined and fixed. So every time an electron enters our island, some other has to go. This doesn't necessarily need to be the same. It has to be the same spin. So we have this effective spin exchange. And this is like, okay, we're sitting on this parabola, we're hopping up and we're hopping down again. And people solved or discussed the system for ES equals 0, namely this Berry and Cooper, because with ES equals 0, their system maps exactly. This system maps exactly to their O4 case. And now our system so differs in ES. So we want to investigate what is the influence of ES. So we can first say, okay, if ES is very large, we have N is J is pinned and N fluctuates, so we can take values on the whole unit sphere. While if ES is very small, J squared fluctuates and N therefore weakly fluctuates, and maybe you can just take some values around the pole. Okay, but large and small is not very physical, so what does it mean? And to make it more quantitative, we introduce a new energy scale. So we now add a term that polarizes the N vector, and therefore we can say, okay, if ES over EZ is much larger than than 1, J squared is pinned in the opposite. And we also looked at this case, but I want to discuss this case here because this is the more interesting one. And what we do is now project down everything to the ground state manifold, and of course do these hopping events in second order. Okay. Therefore, we have our hopping Hamiltonian here. We do these what's called super exchange, so considering a particle hopping on and hopping off again in one turn. And what we end up with is this Hamiltonian. So let's unwrap the whole thing because it's not quite a usual Kondo Hamiltonian. We have, first of all, two kinds of electrons, which is okay because we started off with two kinds of electrons. They're coupling now to an impurity. So here the black ones are the electrons. They're coupling now to an impurity that almost consists out of this J vector, but projected down to the ground state manifold. So it's a vector of Pauli matrices now. And this projector. And this projector is peculiar because it lives in this orbital space. And what it tells us is that if this, when it's in this orbital here, the red one is occupied, then the lead electrons can talk to the impurity. But if it is empty, there is no chance that the two spins feel each other. So therefore, the orbitals act as some kind of gatekeepers for our impurity. And so we have neither a two-channel Kondo, because there is this projector in between, nor have we 2 times a one-channel Kondo. And this is, I think, very interesting. Very well. So, okay, now we want to treat the Hamiltonian. And the first thing we do is we separate in the X and Y, X and Z interactions. So we have the plus and the minus, and in the JY directions here. And then do a Pullman scaling of all of that. So we write down, we did the Pullman scaling, we wrote down the flow equation, and then we looked at the couplings. And what we see first is First of all, they flow to strong coupling, all of them. And second, if we normalize the couplings by the sum of all couplings, we see that they flow to the same value. So they flow also to isotropy. And this fact will be very important later on. Because what we now do with this guy is, okay, sorry. And now we can start to draw some kind of schematic flow diagram. So we know we have this normal topological Kondo effect up here, where ES is much larger than EZ. We have these two channel phase discussed by Invariant Cooper down here. Also, we know, I mean, we calculated it, but I didn't show it because this is not interesting. This point here is stable against perturbations in EZ and has a G of square root of 2 because it's a two channel. And we now have this G theorem that says that always the RG flow goes from a fixed point with higher G down to one with lower G. So therefore, we already have some idea. But we want to now understand this fixed point. So we do the Emery protocol. We bosonize, we unitary transform, and we refermalize. And our final Hamiltonian is then this. And this looks awfully awful. So let me break it down for you. We have, of course, this nice picture. First of all, we have again the neat fermions. Yes.
This theorem is for the C theorem?
Let's say again, please.
Is this theorem for the D related to the C theorem?
I think so. I don't know actually. So I only quoted the theorem. I never really studied it, but I quoted it because it's useful for understanding the phase term. Sorry. Okay. Nevertheless, so we have this Hamiltonian. We have the elite electrons fractionalized, and our impurity is now represented by these four Majorana fermions, which act in both the angular momentum space and the orbital space. So these are composite kind of options. So we see first we have these hybridization terms where Majorana fermions of the island hybridize with elite electrons. We have this term EZ, which couples Majorana fermions within the island. And we have these interaction terms, the green one and the red one. And since we know that if we take an anisotropic coupling and we go from there over a G flow back to isotropy, we can just say, okay, let's kick away the interaction terms. And so we're now dealing with the free model. This is called the Toulouse point in this case. And what we then see is that in the case of EZ equals 0, we have two dangling Majorana fermions. So we will have a G of 2. While once we have any finite EZ, once starts to hybridize in here, and we only have one dangling Majorana fermion, so G is again square root of 2. And this said, we can now complete this RG phase diagram because we know, okay, up here G is equal to 2, and it's actually protected by symmetry. So because of the SU2 symmetry that we break when we turn on EZ, the system will then flow down to, this is what we assume, that the system will flow down to G equals square root of G, actually two-channel Kondo fixed point. Very good. And now, to wrap everything up, we can also calculate some observables. For instance, thermodynamic observables, where we then use, or where we just determined the scaling dimension of the interactions, and we found every term has 2. So this will leave us with a free energy that goes like T squared. And this again leaves us with a thermodynamic entropy that goes like T, and a specific heat that goes like T. So we have Fermi liquid behavior. Different is the situation when we look at the susceptibilities of the impurity. For the J's, we get just constants, while for the case of the X, Y, and Z, so the orbital operators, we find logarithms. So the susceptibility diverges with logarithms, and in Y direction goes like 1 over T. And gamma is a characteristic energy scale of our system. So non-Fermi liquid behavior, great. And the last thing I want to show is the DC conductivity. So we found that at 0 temperature, we have 1 unit of perfect conductance. So we have transport via one channel. And in the higher, like if we go in the regime of high temperatures, our conductivity goes like 1 over the log square root of T over Tk, where Tk is the Kondo temperature. With that, let me just summarize what I told you. That is that we formed this Majorana Cooper pair box and we solved it. So we found the spectrum. We coupled it to leads and found this novel Kondo effect that has a strong coupling fixed point. And we calculated some thermodynamic properties, observables, and we found that it is Fermi liquid, it has Fermi liquid and non-Fermi liquid behavior. So what is left to do? Actually, would like to understand what is the correction to the conductivity with finite temperature, and also what is the conductivity of the spin current flowing through the island. And with that, thank you very much for your attention.
Time for questions.
During the research model,
Yeah.
we had some generic dispersion and a generic superconducting
Yeah.
there, yeah. And then you rotated through these other bases and the kind of practice that it just makes them sort of whole spaces and has a part of objects.
Mhm.
Now, does it, the decoupling of the two Majoranas that you see, which not just now, does it assume some signatures of the original model, they don't have schematic coupling, and like that. So if you put schematic coupling, will they use much of the schematic or not?
Cool. I don't know. I wouldn't know how the operator transforms under this view, like the spin orbit coupling operator. So,
Yes.
Well, one way of, as you probably know, one way of doing the Emery Kickelson effect of preserving the spin isotropy is to do what we call a compactification of the two channel Kondo bond. Do your manipulations work for that case? This is the one way you can do a strong coupling expansion of the two channel Kondo bond. You put your, instead of coupling your spin to two separate channels, you couple it to the spin and the charge of a single channel.
okay.
And since they can never overscreen, you can do a perturbative, a strong coupling expansion of that. So I was just curious as I was listening to talk, whether that trick would enable you to do the second part, to do everything without bosonization. I don't know.
No, I don't know either, but it would be interesting to look into that.
Yes.
Could you do energy as well to compare with the bosonization?
What do you mean, sorry?
Numerical renormalization group?
Ah, okay. I mean, no, I don't know.
Very nice question. So the three and the TRITOPS is timereversal invariant on parameter. So then there are, like, my question is your J corresponds to the sum of some spin from the normal component and the angular momentum of the superconducting state in the second.
Can you speak a little bit up? Sorry.
If I remember correctly, that your J maybe go one slide back.
Yes.
It's L plus S, yes.
Yes.
The S comes from the superconducting state and the L comes from the normal.
Yes. The L, this is the canonical conjugate operator that belongs to this N or D, how it's actually usually called.
Yeah.
And then this S, this is really the spin of the Fermi instance.
I think so. My question is in the context of triplets, when you mention spin or angular momentum of the pair, I usually associate with the non-zero value of Z plus star or N plus N star. So if it doesn't break time reversals, how can you have a time?
And so the way I was thinking a little bit of this J or this L is that if I restrict it to the z-axis, for instance, then I restrict my N to be lying in the plane, right? And then it can tell me something about how many up or down pairs I have in my condensate, and if I sum that all up, then I have a angular momentum, right?
Okay, maybe you're just going to angular momentum in this context in different than the one I'm thinking. Maybe it comes to more about it.
I just have a probably naive question about the theorem related to minimizing G. So it seems that you related earlier the G to the interface. So usually you expect that the interface will be maximized, right?
The interval. So
So at some point you relate entropy to G, the number G, right?
what relate to J?
Yeah, to J, sorry. And there was a theorem mentioning that J is really max.
Ah, you mean, I mean, if I have this term.
No, not this term.
G.
the other one.
G, I'm sorry.
Sorry. Yeah, G. So
You mean, like when I go back to this diagram?
yes, this one. And I think you related G to entropy at some point.
Yes,
So usually we would expect to maximize the entropy, and therefore that is,
you mean this?
yes. So if you maximize the entropy, you maximize the force.
I mean,
I believe in the usual definition of the entropy.
as I said, there is this theorem that says, no, where is it? That usually you flow always to the fixed
Yeah,
point of
exactly.
the load
That's what
G.
That seems surprising to me.
I mean, it means also you go to the
Or maybe the entropy is defined otherwise.
no, I think it's just a thermodynamic entropy, but maybe a way to think about it, I don't know, really, is that the lower the G, the smaller is the degeneracy of the ground state manifold. And in some sense, the robuster is the system, the more robust is the system, right? In that sense, you can maybe understand why you want to go to lower G.
Could I just add a comment on that? I mean, the point is, this is renormalization, it isn't dynamics. We're not letting the system evolve in time and asking what happens to the entropy. We're studying what happens if we look at the system on larger length scales. And so then the right way to think about it is that as you include other terms in your action, they will tend to gap out some gapless degrees of freedom you had previously, which means that will reduce the entropy in the low energy theory because some of the branches of excitation will get,
We got a bit lost. So when you talked about the model after bosonization and rethermalization, right?
This one.
So okay, there is this Toulouse point or Toulouse line where it's non-interacting, right? So, but you said exactly on this line, or how
Yes.
did you incorporate the interactions?
I mean, okay, so what we did was for this consideration, so what is now this G2, what is this G of the system? We were sitting exactly on the Toulouse line, yes. Then later on, for the calculation of the observables, here, of course, we looked at the operators and determined the scaling dimension. And depending on the scaling dimension, you get this dependency, and this was already done for this kind of problems, and I more or less copied from this book. And again, for the susceptibilities, we are on the Toulouse line pretty much, yes. And also for the conductivity, we're sitting on the Toulouse line. But as I said, here we maybe want to look what is here, so there we would need to take the interactions into account.
Yeah, we have time for the last question. Chris.
Yeah, can I ask about going to larger values of G? So you started off with G equals 2 flowing to G equals √2. And then you found this way of having G equals 4 with some symmetry protection flowing to G equals 2. Could I imagine going higher, right? More exchange symmetries. There'll be something that's G equals 6 that flows to, I don't know, 2√2 or something. I don't know what it would be.
I mean, probably what you could do is just put more of these wires on there and then see what's happening then. And then I guess you actually could reach for Hamiltonians where you have more just than two of these dangling Majorana fermions going on. And in this sense, I guess, but we haven't looked at systems with more than one wire yet.
Okay, so yeah, we should end here. Let's thank Steffen again. We are exactly 15 minutes behind schedule.
So we start at 4.
So cut the break by 5 minutes. then.
No, have the break 20 minutes,
Okay.
otherwise there's no way of getting.
Okay, 5 past 4 then.
Yeah.
Thank you.
Or maybe our speaker needs to catch a train, or are you? Okay, then let's do this.
Okay. So